Hello. Check, check. Hello. Check.
Good afternoon, ladies and gentlemen. I'm Sana Sheikh from the School of Technology and Computer Science, and I'll be the compere for today's event. A very warm welcome to the Founders Day 2024 program. Before we commence today's event, I request everyone to put their mobile phones on silent, please, as a mark of respect to the occasion. Thank you for your cooperation. I now invite our esteemed dignitaries, the Director, Professor Jairam Chenglu, Registrar, Colonel Rajiv Anand, and Professor Bhaswati Mukherjee, convener Founders Day 2024, to please join us on stage. We all know that each year on 30th October, we commemorate the birth anniversary of the visionary scientist, Dr. Homi Jahangir Baba, the founder director of TIFR. I would like to invite our director, Professor Chenglur, to come forward and garland the photograph of Dr. Homi Baba, symbolizing our deep respect and gratitude for their contributions. Thank you, sir. Following this, I now invite Professor Bhaswati Mukherjee, convener, Founders Day 2024, to welcome everyone and share her thoughts.
Good afternoon. Director, TIFR, Professor Jairam Chengalur, Registrar TIFR, Colonel Rajiv Anand, Deans, Center Directors, Conveners of Subject Boards, Department Chairs, members of the TIFR Academic Council, esteemed colleagues, members of TIFR Alumni Association, students, and friends. As convener of the Founders Day Committee 2024, it is my pleasure to welcome you to this celebration of Dr. Homi Jahangir Bhaba's 115th birth anniversary. As you know, every year at TIFR on this occasion, we celebrate Dr. Bhaba's multifaceted life through sports events, cultural activity, and scientific talks. As is appropriate for the occasion, today's program is to recognize and celebrate the academic excellence of TIFR, both as a research institute as well as a university. The program starts with a scientific talk on pioneering work being done at TIFR. This will be followed by the academic ceremony in which first the degrees for the past year will be awarded, and then selected members of TIFR will be commended for their outstanding research work and teaching excellence. Without taking more of your time, I welcome you again to this event. Let us begin the proceedings of the day.
Thank you, ma'am. Now, I would like to invite our registrar, Colonel Anand, to share his thoughts.
Professor Chenglur, Director of the Institute, Professor Ghosh, Professor Mukherjee, Convener of the Founders Day Committee, other members, the extended TFR family. It is again a privilege for me to be able to address you as part of our Founders Day celebrations. At the outset, I would like to congratulate the young researchers and scientists who are crossing an important milestone in their career today and are getting their degrees. And it is to them that I would like to specifically address a few thoughts for a couple of minutes. As you would rise and grow through your scientific careers, you will come to a stage where, in addition to your scientific responsibilities, you will take on certain additional administrative responsibilities. And while initially these responsibilities will be closely tied to the functioning of your core scientific purposes, it could be the administration of a lab or a research group. But eventually, I pray and I wish that you would all rise to a position of eminence where you will assume leadership responsibilities. And there, perhaps, for the first time, you'll be confronted with tasks which are purely administrative in nature and have little or no overlap with science as such. And for that future juncture, I just wanted to offer a couple of insights. The first one is that the concept of quality is universal. That is, the quality which underlies all of scientific quest is the same which drives excellence in administrative duties. The American author Robert Pirsig explored this in great detail in his 1970s cult classic, Zen and the Art of Motorcycle Maintenance, where he says that the Buddha or the Godhead resides just as comfortably in the digital circuits of a computer or the gears of a cycle transmission as he does on the top of a mountain or in the petals of a flower. Pirsig was exploring the connection and the conflict between science and arts, but I think we could easily extend that analogy to science and administration and say that the quality which underlies both these fields is the same, but it differs in its application. And again, there is ample literature on the comparison and the contrast or application of these principles to science and to science administration. But I find it useful to refer to the research done by a political scientist by the name of Louis Menzer, who was a professor of political science at University of Massachusetts Amherst. And in his paper titled Scientist as Public Administrator, he says that the scientist and the administrator have their own separate creeds. That is a set of values which get ingrained in them as they grow through their respective fields because they are useful. The scientist, he says, is objective in his approach. He is in the search for the absolute truth. And for him, common sense knowledge is of little practical value. By contrast, the administrator places great importance and premium on common sense knowledge. And he realizes that in day-to-day administrative situations, the quest or realization of the absolute truth is unattainable or at the best an impractical goal. And it's interesting to see how this plays out when both these fields are faced with uncertainty. A scientist tries to tame uncertainty by scientific methods, maybe by something like Bayesian inference or Markov decision process or stuff like that. But for an administrator, he falls back when he's faced with uncertainty on his instinct and gut feeling. And therefore, I would just summarize that while in essence, the quality which underlies both the fields is the same, it differs in its application. And I would say that the reason why we have a very high level of science administration in this institute is that we bear in mind both these commonalities and these differences. Before finish, I would like to extend a word of thanks to Professor Mukherjee and Professor Tole and Professor Bhattacharya, the team at the University Cell and the Founders Day Committee for their efforts in organizing this event. I would also like to give my best wishes and greetings to everyone and the extended family for the upcoming festive season. Thank you.
Thank you, sir. I would like to invite Director Professor Chenglur to address the audience.
Good afternoon, and I'd like to start by welcoming you, all of you, to this function. As we have heard, this marks the 150th anniversary of our founder, Dr. Homi Bhabha. And we have, in addition to the event that we have today, we've also had, as you probably know, a series of events over the last several days. We also have this exhibition outside in the foyer, and I hope that you've had a chance to look at it. It's been put together very nicely by our archive section, and it covers one of TIFR's flagship programs, the balloon-based science. And in case you didn't know this already, this program dates from the time of Dr. Bhabha himself. The focus at that time was the study of cosmic rays, and the program now has expanded vastly to include many areas of science, as well as applications in space research, communication, and even tourism. So some of these programs that we carry out at the balloon facility take forward the research of faculty at TIFR. Other are collaborative programs with institutes, not just in India, but also all across the world. And it's, we are living in an interesting era where there appears to be a rejuvenation of interest in balloon-based science worldwide. And it's very good to see TIFR continuing its very, very long tradition of excellence in this field. This Founders Day event that we are holding today, as you know, is being held very shortly afterwards, after the sudden demise of our long-standing chairman of the TIFR Governing Council, Mr. Ratan Tata. As the council chairman, Mr. Tata played a major role in shaping TIFR and setting the tone and culture of our governance, which the registrar also spoke about a short while ago. His passing away is a great loss to us all, but it's also a call for us to rise to the occasion and make sure that we dedicate ourselves to making sure that this institution continues to hold itself to the highest levels of excellence. One of the areas in which we take great pride is, of course, the training of PhD students. Students have, from the very beginning, been a crucial part of the research program at TIFR. Getting admission into this institute is very competitive. And once in, the students are offered, world-class training programs is what I believe. And, we try and hold them to research problems which are of the highest standards and the highest levels. So today we are here to also celebrate the achievements of these students. I think graduating from TIFR is a great achievement, and I congratulate each and every member of this class. I also know that the training that we offer in the graduate school provides a surprisingly broad range of skills, and I'm sure that wherever our students go, wherever their interest takes them, the skill set will serve them well. Speaking of excellence, we will also be recognizing faculty who have excelled in teaching, as well as the winner of the best theses and other awards. Congratulations to them too. And I'm sure that their achievements will also serve both as a source of satisfaction as well as inspiration to all of us. We are going to shortly hear from Professor Vijay Raghavan, who will talk to us about quantum computing at TIFR, and that also continues a long tradition of FIRST. He's going to talk about the first quantum computer built in this country. And again, as probably many of you know, the first digital computer in this country was also built at TIFR. So I think this is a very apt talk for us to have on this occasion, and I'm looking forward to it and will no longer stand between you and the talk. So welcome again to this event, and look forward to the talk.
Thank you, sir. I now invite our convener, Professor Bhaspati Mukherjee, to introduce today's speaker.
Well, I'm sure all of you would say Vijay needs no introduction, but it's my pleasure and honorable duty to introduce him formally. Professor Vijay Raghavan obtained his PhD from Yale University in 2008. At Yale, he developed a new measurement technique for superconducting quantum bits. He continued to work on improving quantum measurements during his postdoctoral work at the University of California, Berkeley, which led to the first observation of quantum jumps and the first demonstration of quantum feedback in a solid-state quantum system. Since December 2012, he has been the principal investigator at the Quantum Measurement and Control Laboratory at TIFR, where the main goal is to develop superior quantum processors and develop techniques to stabilize quantum states against decoherence. Some key highlights of his group's work include development of a broadband ultra-low noise amplifier for quantum measurements, a novel multi-qubit processor design, and a novel architecture for enhanced qubit connectivity. He is currently leading several projects to build small-scale quantum processors with funding from DRDO, TCS, and DST. He's a recipient of the Ramanujan Fellowship during the year 2013 to 18 that is awarded by the Department of Science and Technology, Government of India, and was recently elected as a Fellow of the Indian Academy of Sciences, Bangalore. So without further ado, I invite Vijay to deliver his talk. The title of the talk today is Building India's First Quantum Computer. Over to you, Vijay.
Thank you, Bhaswati, for the kind introduction, and to the Founders Day Committee for inviting me here to talk about this project, which has been going on for several years. It's indeed a privilege for me to be here on this occasion to talk about this work, and it's an honor to do that as part of Founders Day celebration in remembrance of Dr. Homi Bhabha. So let me wish you all a happy Founders Day and also a happy Diwali and the other festivities in the next few days. So let me get started with the talk. I've chosen the tense of the title carefully. It's not yet complete, but we are almost there. And we had some important milestones in the recent past, and some of you might have heard about it as well. And I will tell you at the end of the talk where exactly we stand and where we are going next. And before I actually get into the meat of the talk, I wanted to... Yeah. I wanted to start by actually acknowledging the huge number of people who are involved in this in one way or the other, for several reasons, because such a big project requires a lot of people. And usually I run late in my talk, so I didn't want to miss this important slide at the end. And of course, I will mention a few specific contributions towards the end of my talk, but all the PhD students who have been in my lab or currently in the lab have contributed directly or indirectly because of various things which built up to this project. The postdocs and the scientific officers, the DRDO scientists who are part of this project, and also the team from the Tata Consultancy Services as well. An important mention to various project students who came for 2 months, 3 months, 6 months over the last several years, but made some important contribution which pushed this project towards the finish line. And of course, the entire TIFR administration, starting from the leadership to my colleagues at Condensed Matter Physics, the various facilities, and the entire administration team, which helps in procuring things, because there are many things to be bought and installed. Also important contributions from outside of TIFR, from these nanofab facilities at IIT Bombay and Indian Institute of Science, and also various colleagues from Mumbai, Hyderabad, IIT Bombay, IISc, and IIM. And the project was funded by DRDO via the Young Scientists Lab, which is this DYSL QT, and also funded by TIFR and TCS. So here I wanted to mention also that there was an Apex committee which oversees the operation of the Young Scientists Lab, and this project was one of the big projects under that. And Professor Sandeep Trivedi from TIFR is the chairman of the committee, and he had really does navigate various things throughout the years. And Ms. Suma Verghese, who is the Director General of DRDO, who's overseeing the operations from their side. So I'll come back to more specific things later on, but let's get started. Before we talk about a quantum computer, we need to just remind ourselves about a classical computer or the conventional computer we use every day, the one I'm using right now, because it's important to see the difference before you can understand why this thing is actually very different and can be very powerful. The fundamental idea behind all of these information processing systems is the fact that how the information is stored and manipulated. So I'm sure many of you know that information is stored in the form of a bit in this binary or digital domain, where everything is broken up into zeros and ones. But these zeros and ones are represented by some physical property, which can vary from device to device. For example, it is a different thing in a compact disc or a DVD on how the 0 and 1 is encoded, some microscopic defects, whereas in a magnetic disk drive, it is magnetic domains pointing in one direction or the other. And similarly for a flash drive or the transistors inside a personal computer, which are either in on or off state. So they all have two physical states, and that is important to remember when we go on to understand what happens in the state of quantum. Now, the reason you have this is, of course, you can do all calculations in the binary form as well. So, you can add numbers in binary form, and you can come up with logic rules for doing that. And the reason this is important is that it is easy for electronic systems to represent these operations in some circuit form. That's one of the main reasons for using this kind of thing. Nowadays, people actually have gone and used systems which are higher than binary. And that is also making sort of a comeback in special areas. But this notion that you can use electronic circuits to carry out these operations is what ultimately allows us to build these machines. So you can use these so-called Boolean logic gates, which can be built out of transistors, which can then be microfabricated in very, very small sizes on a chip. And the big improvement which has happened over the decades is our ability to pack more and more transistors in smaller and smaller area, with the latest processors having billions of transistors in them. And that then leads to these very powerful machines, your cell phones, computers, laptops. And these are very, very powerful. And we use them every day, both for leisure work, emails, scientific research. And we are happy with them. But it turns out that there are still certain kinds of problems which these machines cannot handle. They are not good at it. They are slow at it. And in some cases, they will never be able to tackle them at all. And it is this region where we are trying to address with a new technology, right? So we need actually a new way to compute to do that. What are these problems? And this is where quantum mechanics enters actually in the first place. And this goes back to Feynman when he was talking about using computers to do physics. There's this very famous paper from the 80s and a talk he gave where he emphasizes this point that when you try to solve quantum mechanics, we know the equations, we know how to write them down, and we know how to solve equations on a regular computer. The problem is when you try to do that, the amount of resources you need to solve the problem, that is the memory and the processing power, just blows up so quickly with the size of the problem that it becomes impossible to do brute force calculations of quantum mechanical equations for any reasonable size system, right? If you start from the hydrogen atom, which is the simplest atom in the atomic world, and quantum mechanics was invented to address problems at that regime, you can even solve them by hand. That was a big success of computing the spectra of various atoms, small atoms in the early days of quantum mechanics. But the moment you come to a reasonable size molecule, say the aspirin medicine molecule or the caffeine molecule in your coffee, it's impossible to even store the information in a computer. Now, that doesn't mean that people have not made progress. There are lots of scientists in TIFR who routinely do this, but they come up with approximations to simplify that problem and come up with clever ways to use the classical computer. But in general, any quantum mechanical problem, once it becomes bigger, by bigger meaning more electrons, more number of atoms in the molecule, and then if you want to come to the level of biology or chemical reactions, it becomes very, very hard and nearly impossible. So Feynman recognized that because nature doesn't obey the laws of classical physics, fundamentally it's quantum mechanics, and of course it does obey classical physics in a limit. If you're trying to simulate it, if you're trying to solve it, your method of solution itself should actually be different. You should not be using the classical techniques to do that. And he also realized that it's really a fun problem because it is very, very hard. He had an interesting definition for what is wonderful and fun. Another example, not from the sciences, is got to do with certain types of mathematical problems. What I've shown here are two large prime numbers. So these are prime numbers. And if you ask, a computer to multiply, it'll happen in no time. You can do this on a calculator. And if probably even a school kid can sit for maybe 10 minutes and do this by hand. But if I give you the reverse problem, that is, I give you this answer, and I ask you to find out which two numbers were multiplied to create this answer, then this problem becomes very hard even for computers. So what I mean by that, let's take two prime numbers, 3 and 5. So if I give you 15, I want you to find out which two prime numbers are multiplied. You can do that in your head. As the numbers become bigger, computers can handle it. But once this number becomes very, very large, much larger than what is shown here, then this problem, the amount of time it takes or the number of steps it takes grows very, very quickly, and it becomes impossible. And in fact, what is the significance of this problem? This fact that the reverse problem is hard is used for encrypting all your data. When you carry out a secure transaction, when you enter your credit card details on a website or do an ATM transaction, it uses this to protect your information, because only the person who has access to these two numbers can decode the information, and that person is only you or the bank in some cases, depending on which way the transaction is going. And no other person, the other people only have access to this, so they need to solve this problem, which is essentially impossible once this number becomes big. Over the years, the size of this number has constantly been increased as computers have become more powerful. But computer power sort of grows, in some steady fashion, whereas the complexity or the time grows exponentially. So you just have to make the number slightly larger, and then you're safe again. But this is an example of another mathematical problem, which is very, very hard or impossible for modern computers and will remain so. Now, there is a small caveat here. Someone could invent a classical algorithm to do that. I'm not an expert on the computer science point, whether it has been shown that it is never possible to do this, but I think the question is still open. So the question is that, can we now build a computer which runs by different rules, because the current set of rules don't seem to be enough? And particularly, should they be rules of quantum mechanics? And this hint comes from the fact here that these two problems seem to share this similar complexity issue, that they both the complexity grows very quickly with the size of the problem. So maybe if quantum mechanics can help here, which seems more natural, that if you are trying to solve a quantum mechanical problem, you use a quantum mechanical system to solve it, then maybe such problems can do this. But this was not obvious at all. This discovery was completely a surprise to the community and actually led to the development of these kind of systems. So how do we do this? Okay, let's take a very simple example of an atom with a single electron, like a hydrogen atom. I'm drawing an inaccurate, simplistic picture of what an atom looks like, but this is just for reference. Now we, of course, know that we cannot think about electrons as orbitals in circular orbits, but they are more like wave functions and probability distributions. So I'll make a slightly better diagram here to show these fuzzy circles so that I can be somewhat accurate, but still be simple to explain. How can I use this system? I know this system obeys the law of quantum mechanics. We invented quantum mechanics to explain atoms. So how can I use this to store information? Well, if the electron is found in the lowest energy orbit, I can decide to call that as my zero, just like we have two states in a classical computer. And then if it is in the first excited state, or some other state if you like, you can decide to call that 1. I have now shown these symbols 0 and 1 with these two other symbols next to it to emphasize that these are now quantum states and not the same as the classical states. Otherwise, this would be the same as a classical computer. And this is possible because I'm using these electronic orbitals, which are solutions to the quantum mechanical equation which describes the atom. Now, what difference does it make? The difference it makes is that if you now use this method to store in your information, then you have other possibilities which did not exist. And that is essentially the idea of quantum superposition. What quantum mechanics tells us that if a system can be in a state 0 or a state 1 for a particular system, these are what are called allowed states of the system, then it is also possible to create the system in states which are combinations of these. I'm not writing this in a mathematically faithful form, but essentially you can have combinations of zeros and 1 which in sort of plain language, we say that this quantum bit is both 0 and 1 at the same time. That's unfortunately what the best we can do, because we don't have an intuitive way to explain superposition in this situation. So we say it's both 0 and 1. But it can also be 0 and 1 with a minus sign in between. So this tells you that not just the fact that you can have combinations, the sign or the phase of this also plays an important role. This suddenly opens up a huge amount of possibilities for a system which is storing information in this form, and which is what we now call a quantum bit. So bit is just the short form of binary digit. It is quantum because these superpositions are now possible. Okay. So in general, it can be any two quantum level systems. It doesn't have to be the electronic states of an atom, as we will see some examples later on. And then a general combination, don't worry about these equations. You have 0 and 1, and there is some number in front here, which tells you what kind of a combination it is. It could be that 0 plus 1, it could be 0 minus 1, but it turns out there are actually an infinite number of possibilities, and you can represent them on the surface of a sphere. So imagine this as the Earth. You can say that the north pole of the Earth is like state 1. The south pole is like state 0. These are the equivalent of the classical bit. But you have all these other points on the surface of the sphere, which are all valid superpositions. So you can have your ground state, you can have your excited state, or you can have something in the middle on the equator, which would be an equal combination of 0 or 1. But it could be anywhere here. It could be closer to 1, it could be closer to 0, it could be pointing in other directions. And these are all different values of the numbers theta and phi here. Or if you want to go back to our picture of the Earth, all possible latitude and longitudes, like GPS coordinates, gives you the different possible superposition states this system can take. Okay. So you have an infinite number of possibilities, and suddenly it seems like it's amazing. I can store infinite amount of information, but unfortunately not. Because any storage system, you have to be able to get the answer back. And here quantum mechanics throws a wrench in the works, is that when you measure this system, for example, if you create a system like this, which is midway, which we call as an equal superposition, the answer, when you measure, you ask the quantum bit, hey, what are you? Or what state are you in? You actually get only two possible answers. The answer is 0 with 50% probability, and your answer is 1 with 50% probability. The reason it's 50-50 is because this state is in the middle. If this state was closer to the 1 state, the probability of the answer being 1 will be higher, and vice versa. So now suddenly this looks like all the nice things I was talking about is gone waste, because the answer is still 1 bit, because you're only getting 0 or 1. And worse, it's random. So how can I actually use this? And that's because a single qubit is not enough to do anything meaningful in terms of the power of quantum computing. Okay. So to see that, we have to extend this idea to more than 1 qubit, in fact, a large number of qubits. So let's start by considering n regular bits, right? So if you have 1 qubit, the 1 bit, you have states 0 and 1. So that's 2 possibilities. If you have 2 bits, you have states 0, 0, 0, 1, 1, 0, and 1, 1. That's 4. So if you have n, the number of possibilities is 2 to the power n. And in that system, you can store one of that configuration. You can only have the 0 and 1 arranged in a particular order at a particular time. But when you extend this to n qubits, you now have all the 2 to the n different combinations, but I can now create a superposition of all of them at the same time. This is the key difference. N classical bits, only one of the 2 to the n states. N qubits, I can create the system in a superposition of all the 2 to the n states. This is where the huge difference comes in, and 2 to the n can be very large very quickly. Even for a modest number like n equal to 300, 2 to the n is more than the number of atoms in the visible universe. And you are creating a system which has access to that many number of states in the quantum computer. Okay. And now this is sort of the most complicated part, which even people like me don't fully understand in great detail to explain how a quantum computer actually solves the problem. But the general idea is that because you have access to this very large space, when you do operations on it, many things are happening at the same time. Many different possibilities are being explored. But there is a caveat here, right? You have this very large, and this phase space where all these states exist is called Hilbert space. This is huge, 2 to the n. But the caveat is that when you measure, you only get n bits of information. So all the magic has to happen from the initial part where you have created these huge number of states. And before you measure, you have to do something. This doing something is the quantum algorithm or the quantum program, which manipulates the states of these qubits and then steers it towards the right answer. And this part is very complicated, and it sort of exploits the parallelism of exploring many different things in the Hilbert space, but also the fact that these are solutions of a wave function, so they can actually interfere. Remember, I told you you can have 0 plus 1 and 0 minus 1. So those plus and minus can cancel, or they can add depending on the phases. So that give you a possibility to use the interference to steer your system towards the right answer. Okay, I can understand this is very, very strange, but this is where the power lies. And to do this is not so easy. What I mean by that is that it is not straightforward to take some mathematical problem which is very hard and say, okay, I will do these things and it will get converted into a quantum program. Very few algorithms which have shown this kind of power exist today, which can exploit these features. So there's a big field of research in figuring out how to use this strange set of properties to do that. But we already know sufficient examples that it warrants to do this. And to be able to do this, you need machines which can implement these kind of systems and allow you to manipulate them in a particular way, right? But if we know that, what is the problem in building such a system? It turns out these quantum systems are not so easy to work with. And the basic issue is that these systems don't tend to be stable. What do I mean by that? I just finished preparing my talk half an hour ago. I copied it it was there on my laptop. I came to the venue, and if I found that all of my data was gone, I would not be very happy. So I know that when I store those numbers in my computer, they remain stable at least for half an hour or a few hours. Actually, they can stay stable for years and maybe decades. A quantum computer, unfortunately, today's quantum computers don't typically behave like that, right? So remember, we talked about the states being some kind of a ground state or an excited state. So when you put the system in an excited state, typically what happens? After some time, it wants to come back to the ground state. It's something very natural all systems do. So if you think in terms of information storage, that's terrible. You prepared the system in the excited state, and over some time scale, by this process of relaxation, so for example, an electron could emit light and come back to the ground state, and the state has changed. The information has changed. You have lost whatever you stored before. This sounds terrible. This typically happens on a time scale, which is from the NMR literature, is called the T1 time. And this is also a random process, sort of like how a radioactive atom will emit something at random intervals. This process is random. We cannot predict exactly when it will happen. We can only say that there is a certain chance of it happening over a certain time, right? Worse than this, the fact that it matters for a quantum state whether it's pointing in this direction or that direction. This is the difference between the 0 plus 1 and the 0 minus 1. And these are two different superpositions. So I need to be able to preserve that in a very stable fashion as well. More generally speaking, if I created a state by choosing a point on this sphere, it should remain there. That's what a good state or good qubit would be. But a certain kind of a noise process called dephasing causes these states to become random. So which means that you prepare something, and over some time scale, it becomes completely random. You have no idea what the state is, which means that you cannot use this. And there are certain time scales for this. In the early days of building hardware, these time scales were nanoseconds. Today, these time scales are approaching milliseconds and seconds, depending on the particular system you use. But it's still not large enough, right? If you're rendering a video, it sometimes takes hours to solve that problem. So if you want to solve any meaningful calculation right now, the only option is that it has to be short enough that it happens before any of these bad things happen. So this is a big problem, but thankfully there is a solution in theory. It's called quantum error correction. I won't be talking about this in detail, but essentially it turns out that you can take multiple copies of this, copies within quotes here, to create a perfect qubit from a collection of imperfect qubits. So that is called a logical qubit. And this has been shown to be on solid grounds on theory, that the idea is very solid and proven. And there have been proof of principle experiments which say that, yes, this is in principle possible. It's technically very challenging, and people are still making progress on that. But most quantum computers which exist in the world today do not use quantum error correction. They are all of this type, where over some time scale, they will become random. Okay. Now, to sort of summarize all of this into what a quantum computer actually is, it could be as simple as this: a collection of qubits. The blue circles here represent a qubit. So one of these things which we talked about. And these red connections are telling us that these qubits are interacting in a particular way. They could be created in a linear array of qubits like this, or they could be a square array of qubits with these connections that's shown here. So it's just a network of physical qubits, some objects, a collection of these objects connected together, just like a regular CPU is a collection of transistors which is connected in a particular way, right? After doing that, you need to be able to change the state of these systems. That is sort of part of the programming of this quantum computer. And they should include both operations on individual qubits, but also something called entangling operations, which is involving 2 or more qubits. Typically, 2 qubits is enough. To give you an example from the regular computing, it is like doing these Boolean logic gates, right? You have an AND gate or an OR gate. You need 2 inputs to get an output. Similarly, here you need 2 qubits to do something. And you need a combination of these. And theory tells us that nearest neighbor is sufficient. What does nearest neighbor meaning? That if you take a qubit from here, only the neighbors, if they're interacting with it, it is fine. But if you have extended connectivity, which means that if I could somehow do operation between this qubit and that qubit directly, it is useful. It brings in efficiency. And I will comment on that a little bit later on. Okay. Here is, for example, a layout of IBM's 128 qubit processor. It's not an actual chip. It's just showing same in terms of circles and dashes. And you can see that it's mostly like a linear array, if you follow the laser pointer, with a few cross connections in between. Right? So, and then finally, you need the ability to make measurements so that you can determine the final answer after the programming is over. So you have the system, you have your operations which allow you to program and run the computer, and then you have your measurements to read the answer, right? And the things you're fighting against are this fact that these qubits randomly change state over some time scale, and to make these systems work with larger and larger number of qubits. So here I want to make one last point here before I move on to the meat of the talk, is that a quantum computer is seriously only powerful when you have a large number of qubits. And the reason is that you need that 2 to the n to be big enough that it cannot be solved on a classical computer. Otherwise, you can actually write down the equations and solve it for small problems. So it's only really useful in a practical sense. But of course, you start by building a small quantum computer first. And that's why we also started at a small level in the first place. Now we move on to the actual hardware, and then we'll talk about the 6-qubit quantum computer here at TIFR, right? So there are many ways you can build this. The most common way is to use actually atoms. So this is a trapped ion system where you can isolate individual ions in an electromagnetic field and shine lasers on them to change the state and do the gates. You can also isolate a single electron in a 2D chip called a 2D electron gas. And with the help of these metallic gates, you can create an effective single electron and use its spin, which is pointing either up or down as the states of your qubit. Or you can do something like a superconducting circuit, and this is the field I work in. That is the computer we have built. This is actually an electronic circuit built using superconducting materials. So superconducting metals are those which lose all resistivity or all resistance below a certain temperature. So these are all typically low temperature systems, but they have other interesting properties as well. The point is that all of them have some combination of physical states which you are calling as 0 and 1. So there is no fundamental difference in terms of a quantum computer built using ion traps or superconducting couple. It's only a technical difference. And these are all things which are being pursued in the world today. And there are many other ways. You can use light and use the horizontal and vertical polarization of light as your qubits. There are also something called cold atoms, topological qubits, nitrogen vacancy centers, and many new are being invented. But today, internationally, globally, the leading platforms are trapped ions and superconducting circuits in terms of the largest system built. The photons are making a very strong comeback after a slow start, but a promising start, some years back. So we'll now come to the description of what this superconducting circuit is. Okay. The simplest way of understanding this is that it's actually a pendulum, but in electrical domain. Okay. What is a pendulum? It's an oscillator. You set the system, you take the pendulum and you drop and it will oscillate back and forth, right, with some frequency. The qubit is an electronic version of that, and it's made by taking two components, this symbol called cross, which is called the Josephson junction, and a capacitance in parallel with it. So people who are familiar with electronic circuits, we are calling this as an LC, or an inductor capacitor oscillator. Okay, except that the inductor is a slightly different type, which is called the Josephson junction, and you will see what that does is that it actually gives you the one feature of the pendulum, which I'll just comment in a second. So here's a picture of such a device. So this part in the middle, which I have zoomed out here, and you can see the size scale. This is about 5 microns. This is an image from a scanning electron microscope. This is this circle here with two crosses. The two crosses are here and here at these locations. This is the Josephson tunnel junction. It's two superconductors separated by a thin layer of insulator. And then these two big pads, which are almost sort of hundreds of microns in size, these form the capacitors. So you can see that this system is almost a millimeter in size. You can see this with your eye. Compare that with the atoms and ions, which you cannot see with your eye. So in some sense, it's an easier system to work with, but still it has its own complications. And there is a whole other angle that can such big systems even behave quantum mechanically? And of course they do. That's why we can build quantum computers, but that's a different topic altogether. Here's a zoom in of that Josephson junction. You see there's one metal film here and another metal film coming here. They overlap one on top of each other. And there's a thin layer of aluminum oxide, which is the insulating barrier, which gives this. So this material is aluminum oxide, aluminum, and it's typically made on a silicon or a sapphire chip. Okay. So what is the qubit? It is really whether the pendulum is oscillating or not oscillating. So if the pendulum is at rest, which in the quantum language we say it has 0 quanta of energy, that is the state 0. And if the pendulum is oscillating with the minimum energy allowed in quantum mechanics, so for non-experts here, in quantum mechanics, energy can only increase in discrete steps. So if you go to the minimum energy allowed, that is called state 1. So a simplistic picture is a pendulum at rest is state 0. A pendulum oscillating with some energy is state 1. That's it. That's what a superconducting qubit is. And the Josephson junction actually does something. It actually gives the system nonlinearity. So if I go a little bit into a pendulum is actually a nonlinear oscillator, because when you make it amplitude with large amplitude, it doesn't have the same time period because of the restoring force being proportional to the sign of the displacement. This circuit has exactly the same kind of nonlinearity. Okay, so that is represented here as cosine potential instead of a harmonic potential for the experts here. And that results in the energy levels which are allowed to be non-uniform, like in a harmonic oscillator. And that allows you to isolate the two lowest levels here for your qubit. Some typical parameters are given here. And you have to operate at temperatures much, much lower than this minimum energy. And that leads to the requirement, because we typically make these at around 5 gigahertz oscillation frequencies, which corresponds to a temperature. It is sort of representing energy in terms of temperature of 250 millikelvin. And we use commercial refrigerators called dilution refrigerators to cool down to about 10 millikelvin. And the reason this is important, of course, these low temperatures are necessary to make the aluminum superconducting. But it's also important that this thermal energy does not take you up this ladder. That's random noise for the computer. So if you go to a sufficiently low temperature, the system is expected to be found in the ground state and just remains there and waiting for you to do the operation, as opposed to random signals coming from the environment. So that is a very important reason for going to such low temperatures. And the superconductors also play a role that they allow you to make these systems with as little dissipation, ideally no dissipation. Dissipation here means friction. If you have a pendulum and you set it oscillating, what happens after some point of time? It stops. That is exactly the process of decoherence I was talking about. It went from state 1 and it stopped, it went to state 0. We don't want that. We want this oscillator to keep ringing for as long as possible. So the superconductors help with that as well. Okay. So in order to then do something to these systems, you actually send in a pulse of energy at frequencies which are resonant with this transition. And then you measure. So if you do an experiment where you send a pulse at this resonant frequency and vary the time here, you get these kind of oscillations. This is telling you, and you can get this from the physics of a two-level system, that the system goes from the ground state to the excited state and back. So this actually now gives you a method to control. Remember, we have to program this system. This is how you program. You send in a pulse. So this is a phenomena of Rabi oscillations. The amplitude of this drive decides how fast these oscillations happen. The phase of this drive determines whether the oscillations happen on the sphere in this direction or on that direction. And then the amount of time you send determines how much it rotates. Does it go from 1 all the way to 0? Or does it go from 1, stop somewhere in the middle or elsewhere? So you can now see that by choosing the right pulse, I can put the system anywhere on the sphere, which is exactly one of the things I wanted to do. Okay, so you can create all the possible superposition states. To finish the story about the elements that you need, I also need to create interactions. Remember, I told you qubits are the circles, and I need to create these red things for them to interact. How do you do that? You take 2 qubits and you put a capacitor in between. So this is like an electrical oscillator. This is another electrical oscillator. I connect with this capacitor. I've shaded this because it can be something else as well. So here are 2 examples. Here is a chip from IBM from 2016. These parts here are the qubits. And instead of a capacitor, which typically requires them to be right next to each other, you have something called a microwave transmission line labeled here as a bus. It's called a bus cavity. This allows you to keep the qubits separated and still create interactions between them. So it's basically a way of creating electromagnetic interaction. This is called a fixed coupler because its strength is fixed by design. Once you connect it, it's always there. But you can also create more complicated circuits. Don't worry about the details here. But here are the qubits, these plus-shaped things, and there is a more complicated circuit which are now tunable, which means it's like a switch. I can turn on the interaction and turn off the interaction. This is more ideal, but this is doable and easier, and this is actually what we use in the experiments we have implemented here. Okay, so it's sort of like a coupled oscillator system, and again, you use a microwave frequency pulse to create this interaction and do 2 qubit operations. Let me just check how I'm doing on time. Possibly what's time single time? 15 minutes? Okay. So now we start into actually building these things. Here's a picture of the dilution refrigerator. This part here is what gets to the lowest temperature of 10 millikelvin, right? This system is about this tall. That's the size scale you're seeing here. And there are many, many components. You have to send these signals to various cables. You have to attenuate them. You have to filter them. I'm not going to explain this. The idea here is to give you a sense of the complexity of building such systems. This amount of components is needed to control 1 qubit. Here is the same component diagram for 4 qubits. There are probably some 50 components already here. So imagine a real practical quantum computer which may need thousands or millions of qubits. The number of these components is going to be huge. There's a huge challenge in miniaturizing this, how to do it in a more efficient fashion as well. Okay. And once you do all of this, at the end of the day, the quantum program looks like this. So read this from left to right. Each of this line is one of the qubits. This is showing an example for 5 qubits. And each of these boxes represents one of these operations which you're doing to program the computer. So boxes which are on only one line, these are single qubit operations, and boxes which connect, or symbols which connect 2 lines, these are 2 qubit operations. each of these symbols here, in practice, in the superconducting qubit architecture, is implemented by a microwave pulse of a particular shape. So you have to figure that out. You have to train and then ensure that it is doing the operation it is designed for. And this whole thing has to be periodically checked because the parameters drift and you have to keep doing that. So at the end of the day, a quantum computer is a collection of superconducting qubits, in this case on a chip. It's sitting in a cryogenic environment, and then you send in a whole bunch of microwave pulses to program it and to measure it at the end. So these are the final step is you measure and determine whether the answer is 0 or 1. And hopefully, if you have done everything right, those zeros and ones are meaningful to the problem you're trying to solve. Okay, so we'll now come to the thing we have actually built here. This is sort of an overview of what the full system is. There is now much more than the actual quantum hardware. It starts with the cloud access that you can actually program this from your web browser. That information is then given to a computer in TIFR, which takes that in the circuit form like you saw earlier and converts it into a form which is compatible with the hardware we have built. That then goes and programs a bunch of electronics which prepare those microwave pulses so that they can be sent to the quantum processor. The quantum processor is sitting inside this cryogenic setup and receives those pulses, and then the results are sent back over here. And they go back to this software and back to the cloud access to display the answer. This is the full system we are talking about. In sort of common parlance, is often called as the full stack system. Every part of this thing has to be built. So you can see some pictures here. This is the picture of the quantum processor unit, which we have built. You will see more details in a little bit. It is mounted inside these shielding environments in the dilution refrigerator at the 10 millikelvin stage. And here is the full picture of the dilution refrigerator, which is now closed up. What you're seeing is the vacuum can. And then here are all the electronics which are needed to control it. And there is a computer sitting, a regular classical computer sitting elsewhere, running all of these things. And then you also need this automatic calibration software, which makes sure that it keeps everything running here. So often people, ask me, show me the quantum computer, right? Some people think that this is the quantum computer. Some will say, no, that's the quantum computer. But actually, this full room of electronics is the quantum computer. This is really just like this equivalent of CPU. Just like if somebody has a CPU in their hand, you cannot use it. You need the motherboard, you need the powers, everything to use the full quantum computer. So today, quantum computers are not compact objects which are sitting on your tabletop. They are room full worth of equipment. That is not something which is going to stop, because for most typical applications, these things will be accessed over a cloud. So you can really think of them as supercomputing in cloud-based centers where you can access them remotely. And that model works quite fine, unless there are some security reasons for which you might need this in your backyard. Let's look at this in a little bit more detail. So here is the QPU here, and each qubit here is a separate chip. And this is based on an architecture. This is unconventional. I will explain to you why we did this, which was invented in TIFR by one of the students here. And you can see this chip here. This is the chip. This is about 9 millimeters, or so about 6 millimeters long here, and about maybe a millimeter or so this direction. And you can see these shiny parts. These are the capacitor pads. And the Josephson junction is right in the middle, which you cannot see. And there are 6 of them in around this circular circumference here. And they create a processor architecture which looks like this. So you see here, and this is one of the unique features of this architecture, that it has this non-nearest neighbor connections. So this qubit is connected to these 2 neighbors, but also crosses across to the other side as well, right? And this is one of the things which came out of the thesis of my student who graduated a few years back, is that we found out that instead of laying this out in a 2-dimensional grid like this, if you distribute the qubits along a circular path, a circular connection, then it is possible to create a system which has connectivity actually of this form. So this calculation and testing was done for a 12-qubit system, where we showed that if you put them around a circle, each of the qubits actually can interact with 9 other qubits, as opposed to only interacting with their nearest neighbor in this line. So this is, as I mentioned earlier, this is an important feature. This architecture is still work in progress, but we demonstrated this in paper that the basic idea works. And since this was robust enough, we decided to use this for our 6-qubit system here. So here you see this in a zoomed out thing. The circle here in the middle, that's the circular path here. And all these chips sitting here are connected to that common circular path, which allows them to interact with each other, even if they are far away from that, okay? Some size scales for you and to comparison with how typically these systems are built. This is actually a piece of aluminum made in our central workshop, right? It's machined in our central workshop, and it's about 75 millimeters across. And this can potentially house up to 12 qubits, but we are doing it with 6 qubits. This is a 5-qubit chip from IBM from 7-8 years ago, and this size is about 4 millimeters or so, right? So our system is much bigger. But the reason for that is that the current fabrication facilities we have and the methods we have optimized is not reliable enough for us to make this chip and ensure that every part of this has exactly the right parameters. Whereas here, my qubits are separate. Each qubit is a separate chip. And this is a machined piece of cavity, and our central workshop does a really good job to make it accurately. So once it is made, it's fine. There is no errors in there, right? We can do some fine tuning, but it's ready to go. So this allowed us the option that because we cannot very reliably yet produce these qubits with the right parameters, it turns out that we have to choose these parameters very carefully. It allowed us the possibility of coming up with 6 qubits, which we can put in by making about 50 or 100 qubits and picking the 6th best one. Whereas in this case, a single chip has to have everything correct. I cannot, take out a bad qubit and put a good qubit. So this was something which allowed us to play to our strengths and allowed us to get to a stage without having to have the more sophisticated facilities, which hopefully will come up in the future. So this was a choice, and because it's modular, if one of the qubit goes bad, I can just open it up and change the qubit. Right? It's equivalent to saying that you have a CPU with billions of transistors, and one transistor goes bad, you remove it with a new one, and it starts to work. It's kind of an extreme example of that. I will also point out that this architecture, this approach is not scalable for building qubits systems with thousands or millions of qubits. But as a prototype, this is a good way to start. Okay. So in the last few minutes, I'll quickly summarize. So this is how the architecture looks like. We were able to put these 6 qubits, measure how they are interacting. So these numbers actually tell us that the interaction between the qubits is as expected, shown by these solid black lines. And these dashed lines are the ones where they're not supposed to be interacting. Those are the weak numbers here, and they behave as expected, but we need to optimize this further. This will come back to the point on where exactly the status of this thing here, right? So finally, when this thing will be launched, this is what you will see. You will see a homepage where you can log in after registration, and then you will be able to get to a page like this, which allows you to draw the quantum program. So you can these are small enough that you can drag and drop them and create a quantum program using these blocks. Each of these blocks corresponds to one of the operations I talked about. And then this system then gets executed on the hardware. To do that, we had to do a bunch of things. So that original diagram gets converted into a format which is compatible. It's sort of like saying that there's a different operating system here and the input language is different, so I have to translate it correctly. Then this has to be converted into a program. So it's like one program writing another computer program so that the electronics can understand what to generate. So here's an example of that. Of course, you cannot see this. And then finally, that electronic program runs on the electronics and creates the pulses, and that generates the output result, which then goes back and gets displayed on the server here. So it will be a web-based system which you can access. And the big news which happened about a month or so back was that we were able to test this full thing for the first time where every component was working. Okay. So this is the current status, right? We have been able to draw these things, and we have been able to create results like this. For example, here it's showing a 2-qubit circuit which creates what is called an entangled state. And this result shows that this creating an entangled state. It's not perfect. If it was perfect, these little bars here would be 0, and these bars will be exactly at 50%, right? So we have done this, what is called end-to-end testing, but what is left is that we now have to replace qubit chips because, as I said, the parameters of the qubit are not exactly optimal. We can do better than that. So we are working on making better qubits there. We're also improving the measurement. So this is a technical term, readout fidelity, but essentially when you measure a 0, you should measure it 0 without any error. Turns out that is also challenging. So we're adding some components to improve that. These components are ready. And in fact, an experiment is being prepared today to test this. I was actually hoping that I will actually show a live demo today because the system was operational. But thanks to that very special power cut over the last weekend, the whole system shut down. And then we decided that it doesn't make sense to start it over again because the time was too short. We also want to improve these shapes of these microwave pulses so that they can do their operations more precisely. We want to finally finish this automatic calibration software that once we let the system run, it will take care of itself. It will not need manual intervention to correct it. Also test long-term stability, that it runs in a stable fashion over extended periods, and then figure out the cloud access logistics, which is like, who can register, how to register, how many people can be allowed. Initially, we will open it up to a small number of selected sort of partners while we're doing sort of testing, and then eventually it will be open up to everybody. And then it will sort of become the first Indian quantum computer available on the cloud to be used by anyone. Okay. So before I end, I just wanted to say, a few challenges and some anecdotes. I'm sure many of you have, and my fellow colleagues have faced these challenges, but these all added to the fun and the misery of this entire process, which has been happening over the years. The one I want to emphasize, and the others I will just run through, is the science versus engineering project. Right? This is really an engineering project in the sense that we have not invented new things deliberately here because many of these things have been done elsewhere in the world. So it's not an optimal project for a PhD student. And this is one fundamental challenge and question we face, and we are actually still facing as we go to the next stage. So it took us some planning to figure out that, okay, we're going to get scientists and engineers from DRDO to help us with the engineering aspects. And we introduced this novel architecture so that some new science can also come out in form of this ring resonator-based experiments. So this is an ongoing challenge for the whole country, actually, as we go forward in developing these technologies. The global pandemic started exactly at the start of this project. So for about a year and a half, we could really not do anything. The global pandemic resulted in the government introducing lots of new procedures and rules, which made buying things very, very difficult and slowed down the progress quite tremendously. During the pandemic, a lot of equipment failed, which typically does, but usually it's repaired quickly. But during the pandemic, we could not repair those things quickly. So this, again, was a huge problem. Fabrication uncertainty, I already mentioned that our fabrication is not precise enough to do this, and it varies a lot. And this was particularly a very challenging thing because when we finally started to make the last batch of qubits before we did that demo, we fine-tuned everything, and then we said, okay, now we will produce some 50 qubits, and then the very next first step, everything drifted again. So, these are some realities of doing these kind of experiments. And the last is another important point is that for executing these kind of projects, you cannot only work with the typical kind of people you have in an academic environment. You need engineers who are dedicated to doing that. We are not necessarily going to create new knowledge all the time here in the early stages as we are solving the engineering problems for ourselves. So we have to find ways to attract and retain the talent so that they don't disappear after working for a few months. Okay. But despite all of these challenges, the team worked on. So this is sort of the members of our lab over the years, a lot of them here who have contributed in various ways. And so they persevered, and it is because of their hard work that this has happened. My job these days is mostly to give talks and receive applause, but these are the real people who are actually doing the job. I don't want to, say that a particular contribution here is less or great, but I do want to point out a few key people here who were instrumental to this particular project. So Sumeru Hazara was the PhD student whose thesis invented the ring architecture, and he set off the first round of experiments. And then it was taken over by Jay, who's currently the lead PhD student executing this project, along with DRDO scientist Binoy, who's been resident at TIFR for the past 2 years and working with us. one of the challenges I mentioned to you was the coherence of these qubits. We used to make these devices out of aluminum only. Some years back, it was shown that if you use different superconductors like tantalum, you can improve the coherence times. And we were suffering with the coherence times not being so great. So Srijita here single-handedly developed this process over the last 2-3 years. There was a lot of crazy stuff and difficulties here because we didn't have the right equipment. I was going to tell that story, but I don't think I have time. But essentially, I've been trying to buy that right piece of equipment for the last 10 years, but I have not been able to do it. It's nobody's fault. It's just a combination of bad circumstances. And finally, with the help of a borrowed equipment from one of our colleagues, she was able to do this, and it completely changed all the devices in our lab. Every experiment started performing better because of this new process. So a big thank you to her. Madhavi is our resident sort of long-term postdoc who's been taking care of the overall fabrication. So she comes in and trains all the new students and coordinates the whole fabrication activities and including the development of the amplifiers. Gautam, Anish, and Apurva were 3 project students who came for relatively short periods of time, but gave serious impetus to the project. So Gautam, in the early days of the ring, did the calculations to figure out what the qubit frequencies should be in this ring architecture to get the best performance. Anish and Apurva worked on the software aspects. Anish was focusing more on figuring out how to automate various aspects, and Apurva actually wrote that important part of the thing, which created the program so that the electronics could understand. And I just met him on the seashore one day where he just ran into me and said, hey, I want to work in your lab. And it was just like, a coincidence, and it worked out really well. He was here for just a few months, but he made that important thing. So thank you, a special thank you to all of these guys. Just in the last couple of minutes, what's next is that now India as a whole is investing hugely in this technology. So because of all of these efforts, this happened about a month back, where I'm receiving this little thing here, which is that thing. I will explain that in a second, where we were awarded this project to build superconducting qubit-based quantum computers, 24 qubits in 3 years, 100 qubits in about 5 years. So there was actually a ceremony. I don't know when was the last time somebody got a memento for winning a grant. I think the government is also going big gun. So this was an interesting experience. And the rest of the people here are the team members. So this is what is called as the technical group on superconducting qubits under the National Quantum Mission. It comprises of 8 PIs. So I am the lead investigator leading the project from TIFR, where the 100-qubit quantum computer will come up. And so these circles represent these cryogenic stations. There'll be an R&D station. IIT Bombay has an expert who does the 3D ICs and packaging and a theorist for the optimal control. IISc Bangalore also has 2 stations. The 24-qubit quantum computer will come up there first, along with an R&D center. They have 2 experts in superconducting qubits and 1 expert in control electronics, which we are also hoping to now develop in an indigenous fashion. We also have a new faculty at TIFR Hyderabad, who's an expert at superconducting circuits, and he will be running an R&D test facility there, along with development of quantum memories, and then another theorist from IIT Madras for the quantum error correction part, which I had very briefly mentioned. In addition, there are going to be central fabrication facilities. Spokes and Spikes are other partners who are going to come externally, other groups which have been funded to collaborate, also interactions and collaborations with industry and startup and international scientists. And all of this is, of course, going to have human resource development, outreach, and also reaching out to venture capitalists to raise more funds for doing maybe some final practical thing here. So this is sort of a summary of the next step under the National Quantum Mission. And we have been lucky to get this project, and we are looking forward to this. So to summarize, I hope I have shown you that the superconducting oscillators can work like qubits. We talked about how the qubits can be controlled and measured using these microwave pulses. A lot of cryogenic signal processing, filtering, and shielding is needed. And I showed you about what the 6-qubit quantum computer is and where we are today and what we hope to achieve in the near future. To summarize sort of the Indian efforts in this landscape, there are actually early NMR experiments at IISc Bangalore, which used nuclear magnetic resonance to run quantum algorithms. But this is now no longer considered a practical way to scale up to a large number of qubits. And without large number of qubits, you cannot gain any useful advantage of that. Then in the early years of our lab, we invented a new type of 3-qubit processor. This was the first thesis from our group. And then now we have this 6-qubit processor under development. But there are other superconducting circuit labs. As I mentioned, there are 2 at IISc, 1 at TIFR Hyderabad, and 1 at a private university in Kolkata called PCG Crest. And I have been helping them set up their research program over there for the past 3 years or so. We also have other platforms using semiconducting qubits at IIT Bombay and IISER Trivandrum. One group at IISc had very recently demonstrated a 6-qubit experiment. It's not a 6-qubit quantum computer in the same sense. It's an experiment using light. So it's a photonics demonstration. And there are new labs which are coming up for ion-trapped cold atoms in photonics in the country. And one other thing which has been happening in the last few years is that I've been working with a team from BARC who are actually working on various aspects of quantum computing, which includes fabrication, it includes control electronics, and also software. So there is recently they put out some newsletters giving an update on the activities they have been doing. And I'm actually looking forward to keep this collaboration alive as we go into the National Quantum Mission, because we're going to need a lot of people to get these things going. And that will allow us to build these bigger processors under the National Quantum Mission. So with that, let me thank you, and I'll be happy to take the questions in this time.
Thank you, Vijay. I think we'll have a few questions. So there are probably volunteers with microphones. Please raise your hand. Yeah, Prahlad.
Thanks for a very committed talk. Couple of questions on the ring resonator. So, first question is, what's the advantages of the ring resonator over the usual grid architecture? Is it the fact that you can have larger sets which are entangled with each other? This one, and other is, how do you right now the ring is consisting of 6 qubits or so. How do you plan when you want to scale up? Will it be several rings talking to each other, or going to be larger rings? Or
yeah, you've actually answered both the possible outcomes. But essentially, yes, that's the idea. See, if I had broken this ring and I had just put this in a linear chain, then because of the way these things are connected, it is only possible to create these so-called entangling operations between the qubits which have direct connection. And that is something referred to as connectivity in the architecture. So if I look at this square grid, and suppose my algorithm requires that I need to do an entangling operation with this qubit here, with that one. It's not that it's not possible to do, but you have to do it in many more steps. So you will have to go via these intermediate qubits to reach that qubit. So more steps means more errors and hence poorer performance. But if there was a direct connection, if there was a red wire going from here to here, which typically in a 2D thing is hard to do, though you can have multi-layer PCs and people have tried, but it turns out that translating the standard techniques in semiconductor fab to superconducting things doesn't always, because these things introduce these microwave losses and things like that. So we were trying to solve this problem that I want to retain a planar architecture without any crossovers, then what's to do? And it was motivated by how trapped ions use a common mode to communicate between distance qubits. So we came up, it doesn't work exactly the same way. We came up with this circular transmission line, which actually mediates the interaction between them. And it gives you a connectivity as shown by these lines. So the lines represent the actual interactions. So you have strange things like the interaction, the qubit 12 interacts with qubit 6, but does not interact with qubit 4. In fact, it interacts more strongly with qubit 6 than compared to qubit 1. And that's because of wave interference effects here. So that's the thing. Scaling up is challenging. It can be a combination of a larger ring with smaller angular spacing or collection of rings with connections in between. Both of these calculations we have done in that first paper, but they are quite hard to implement practically. So we are still, that's still in the R&D phase. It's not really ready for prime time for scaling up to a large number of qubits.
Just question again, ring structure. So you have
Take your mic closer. I'm not able.
So related to the fact that you have more connections, so in the INDIC, the sort of gates that we can implement, which can program later and do. Does it also allow for a richer gate structure because you have these much more entanglements over pairings over here, or is it the usual gate structure that one? The basic.
Yes, so that's a nice question. As of now, the gates are standard. The only difference is that I can now do gates between these shown connections. But I think what you're alluding to is that you actually have more than 2 qubits interacting at the same time. So you could, in principle, have a fundamental 3-qubit gate or a 4-qubit gate. These are possible. We have not gone exploring in that directions yet. It is sort of there in the long-term agenda. They tend to get more complicated to optimize. So we have stuck to only 2-qubit gates for now.
Thank you.
Any further questions? Okay, Satya has. Dipasha, please. Here's a
there.
question.
Mike, it's not on.
Can you hear me now? Yes. Okay. Vijay, fantastic lecture for non-starters. One thing that I just happened to see, and I wanted to ask you this is in the photonics regime. I just heard that somebody kind of built the world's smallest quantum computer with using single photon. How is that possible?
Well, single photon is the equivalent of a single qubit. But depending on exactly how you're doing, these. Sorry, what happened? Those photons can be made to split in beam splitters and go along multiple paths. And that can sort of effectively create more qubits. But we can also use other degrees of freedom. So for example, I mentioned that the standard way of doing it is horizontal or vertical polarization. But people have also tried to use higher order states like orbital angular momentum states. Essentially, you need some physical property. So if you actually carefully looked at our qubit, it's not a 2-level system. It actually has many levels. So we could also actually create a 2-qubit system from a single physical device as well. So it's sort of in that sense, I think they have used some higher order states. I remember seeing this news, but I have not read it very carefully. But it is possible to do that. And now with the photonic integrated circuit architecture developing quite strongly, these photon-based computing systems are actually showing some progress. And people have also built massive systems in China. They have built some fairly large things, but they are right now fine-tuned for specific kinds of problems. They are not what are called universal quantum computers. The kind of architecture I talked about falls in the category of universal quantum computers. So as long as the program, the algorithm can implement that problem, you'll be able to run it on these machines. Some of the photonic systems are specific to certain kinds of problems. But these are all, small details which people are trying to solve.
Well, thank you. I think we would like to continue this discussion, but in the interest of time, I'm sorry to have to close this session. Let's please join me in thanking Vijay Raghavan for sharing
so much.
such great insights of his lab and also sharing the exciting future ahead.
We now move forward to the second part of this program to appreciate the academic achievements of our students. In absence of Professor Shubha Tole, Dean Graduate Studies, kindly join me in welcoming Professor Arnab Bhattacharya, Center Director of HBCSC, on stage to announce the academic degrees.
Okay, so welcome to this part of the program, which is the equivalent of the TIFR deemed to be university's convocation ceremony, where we recognize all the degrees that have been awarded in the last year. And I will just read out the names of all the people who have received PhD and master's degrees from the deemed university. So PhD, we have Aditya Vijay Kumar, Arnab Roy, Varun Maiti, Junaid Majid Bhatt, Kallol Pal, Mohammad Sabir Ali. Mohammad Abdul Kalam Adad Siddiqui, Parshwanath, Piku De, Sarthak Duari, Satyani Bhadra, Siddharth Dhanpal, Soumyajit Mandal, Shovik Sasmal, Shrashti Goel, Trakshu Sharma, Tuhin Ghosh, Vikas Saini, Abhradeep Roy, Aman Kumar, Anup Mutneja, Vishwadeep Das, Chandramouli Chaudhary, Devajyoti Kanshabanik, Krishna Chandra Joshi, Muhammad Mursalin Islam, Mintu Kumar, Prasad Subramanian, Pranobesh Maiti, Ravi Shankar Shamanta, Sagar Hazra, Shanat Ghosh, Sanjeev Kumar, Savani Datta, Shubham Singh, Sham Sundar, Shaumen Das, Shaumen Haldar, Shubhajit Sinha, Sugan Durai Murugan Vel Aragan, Ayush Nema, Pranoy Verma, Sonalika Purkayastha, Tanushri Jana. Moving over to chemistry, Abdul Wasim, Anushtup Chakraborty, Praveen Pralhad Tavre, Sunandita Pal, Abhishek Kaur, Arpan De, Debanjana Das, Ravinder Kumar, Rohit, Shubhendu Pandit, Suman, Ved Prakash Tiwari, and an MSc, Krishan Gopal. Moving over to biology, PhD, Anupam Singh, Atulya Girish K, Basil Turakkal, Deepanshu Suta, Fauzia Kaleem, Ayyar Swaminathan Krishnan, Manaswi Raghuram, Meha Praveen Jadhav, Piyush Daga, Purnati Khuntia, Rahul Kumar, Rupam Bhattacharjee, Sandra U.S., Shankhanil Saha, Shaurav Varal, Shweta Chakravarti, Sriram Narayanan, Suraj Raghunath Chakravarti, Utkarsha Ghai, Varun Suresh, Vikas Ram Yagya Tiwari, Vinay Sagar, Vivek Hari Sundar Gandhi Vel, Zubin Rashid. Int PhD Biology, Alok Verma, Abhishek Sharma, Anubhav Prakash, Anurag Kumar Singh, Anvesha Guru, Darshana Kapdi, Kambadur Gundu Anantamurthy, Mahima Bose, Nitish Malhotra, Rajit Narayan C, Rashmi Agarta, Subhash Lal Bahadur Khatri, Sunaina Sharkar, Toshali Banerjee, Vidur Sabharwal, Arun G.S. MSCs, Chittaspandini Gopal Kulkarni, Debapratim Sheel, Debarpita Datta, Devashis Sen, Harshavardhan Bomma Shetty Halli Nagar Rajaya, Ishita Talwar, Mayank Gupta, Meghana Nandi, Nikita Goyal, Prachi Bhatia, Pratiksha Mal, Shemanti Das, Shreya Kandpal, Shreyam Chaudhary, Sham Sundar Nilesh Budh, Shuparno Das, Shri Padmapriya Boyana Palli, Tanushri Umesh Pathak, Urvi Mishra, Yukta Khurana. Moving on to mathematics, PhD, Pinak Mandal, Sagar Srivastav, Samir Kulkarni. Int PhD mathematics, Akash Parmar, Anand Uday Chit Rao, Arpit Babbar, Harsh Prasad. Mohit Upamanyu, Ramya Datta, Shiv Shankar Sinha, Shrikant Pai. MSc Mathematics, Adi Bhure, Ashutosh Roy Chaudhary. Computer and System Sciences, PhD, Kumar Saurav. Computer and System Sciences, Int PhD, Neha Sangwan, Sunil Saraswat. Computer and System Sciences, MSc, Praveen Sai Chinta Ginjala. Science Education PhD, Charudat Sharad Navre, Jayashri Subramanian, Meera Kharatmal, Rafiq Rashid Sheikh, Sujata Varadarajan, Saurav Shom.
Thank you, sir. I now call on this, I now call directed on stage. The TIFR Endowment Fund have instituted best thesis commendations for the year 2024. I request Professor Arnab Bhattacharya to please announce the names and the director, sir, to give the commendations. Thank you.
So these are the best thesis commendations and the honorable mentions in various subjects for the year 2024. We start with physics. The Geeta Udgaonkar Best Thesis Commendation in Physics 2024 is presented to Dr. Shubhajit Sinha for developing a new experimental method to prove the Berry curvature dipole associated with the topological properties of band structures. The next. Yes. So may I request those who are here, or if your parents are here, please come in front so we know that we can invite you to the stage. The next Geeta Udgaonkar Best Thesis Commendation in Physics 2024 is presented to Dr. Tuhin Ghosh for insightful computational studies of mechanisms for formation of planetary systems. I don't think Tuhin is here, so we go ahead. He's online. Okay, congratulations, Tuhin.
Thank you.
In physics, we also have a honorable mention. The Geeta Udgaonkar Best Thesis Commendation in Physics 2024 honorable mention is presented to Dr. Muhammad Abul Kalam Azad Siddiqui for the experimental investigation of matter wave diffraction and the two-center interference effect in ion atom molecule collisions. Not coming. Okay. There is another Geeta Udgaonkar Best Thesis Commendation in Physics 2024 honorable mention. This is presented to Dr. Sugan Durai Murugan Vel Aragan for insightful studies at the interface of turbulence and statistical physics, including questions of thermalization in hydrodynamics. Also not coming. We move on to biology. The Dr. Zita Lobo Memorial Best Thesis Commendation in Biology 2024 is presented to Dr. Iyer Swaminathan Krishnan for his theoretical work on how distributed cellular systems locally process noisy molecular information to achieve a global task with high fidelity in development and cell signaling. Coming. The Dr. Zita Lobo Memorial Best Thesis Commendation in Biology 2024 is also presented to Dr. Sriram Narayanan for his work on developing instrumentation that led to discoveries regarding the neural mechanisms in the cerebellum underlying predictive sensory motor decision making in zebra fish using innovative techniques. The Dr. Zita Lobo Memorial Best Thesis Commendation in Biology 2024 Honorable Mention is presented to Dr. Vivek Hari Sundar Gandhi Vel for understanding the molecular aspects of a directed chromatin demarcation pathway and the discovery of a novel histone H4 variant in plants. Moving over to chemistry. The Best Thesis Commendation in Chemistry 2024 is presented to Dr. Ved Prakash Tiwari for developing a transformative set of new nuclear magnetic resonance methodologies that were used to derive information on sparsely populated protein folding intermediates. And Dr. Ved Prakash is here. The Best Thesis Commendation in Chemistry 2024 Honorable Mention is presented to Dr. Abhishek Kaur for pioneering contributions in peptide and protein chemical engineering and for the development of innovative inhibitors targeting disease-related protein-protein interactions. We have another Best Thesis Commendation in Chemistry 2024 Honorable Mention. This is presented to Dr. Shunandita Pal for her fundamental contributions to confined photochemistry and organic photocatalysis in water. Jyotishman? Moving to mathematics, the Harish Chandra Memorial Best Thesis Commendation in Mathematics 2024 is presented to Dr. Vedansh Arya for deep and significant results in regularity and unique continuation theories for partial differential equations. The Harish Chandra Memorial Best Thesis Commendation in Mathematics 2024 Honorable Mention is presented to Dr. Anand Udaychit Rao for deep and impressive contributions to the study of local Galois representations using rigid analytic geometry and p-adic Hodge theory. And his parents are here. The Harish Chandra Memorial Best Thesis Commendation in Mathematics 2024 Honorable Mention is presented to Dr. Ramya Datta for establishing the radial symmetry of positive solutions of a quasi-linear elliptical partial differential equations in hyperbolic space. The Best Thesis Commendation in Science Education 2024 is presented to Dr. Sujata Varadarajan for her investigations on the use of problem-based learning in undergraduate chemistry laboratories in India. The Best Thesis Commendation in Science Education 2024 honorable mention is presented to Dr. Jayashree Subramanian for her work on mathematical explorations with socially marginalized students and proposal of coherent formalizability as a suitable acceptability criterion for mathematical discourse in classrooms. Moving over to Computer and System Sciences, the Best Thesis Commendation in Computer and System Sciences 2024 is presented to Dr. Neha Sangwan for her work on a general model for addressing the important and difficult problem of communicating securely and reliably on a multiple access channel in the presence of adversarial nodes using tools from information theory. Her father is collecting the award. The Best Thesis Commendation in Computer and System Sciences 2024 honorable mention is presented to Dr. Shubhata Agarwal for providing a fine and impactful analysis of multi-armed bandit problems when their payoff distributions are heavy-tailed, when even second moments don't exist.
We now continue with B.M. Udgaonkar Excellence in Teaching Commendation for the year 2024. Professor Arnab will announce the names and read the citations, whereas Director will hand over the commendations.
The B.M. Udgaonkar Excellence in Teaching Commendation in Physics 2024 is presented to Professor Prasad S. Perlekar for offering well-structured courses with a balanced content of theoretical principles and practical applications.
Thank you.
B.M. Udgaonkar Excellence in Teaching Commendation in Biology 2024 is presented to Professor Rajesh Kumar Ladhar for teaching developmental biology using novel methods like visualizing complex phenomena as origami and inspiring students to carry out research in this field. The B.M. Udgaonkar Excellence in Teaching Commendation in Chemistry 2024 is presented to Professor Jagannath Mondal for engaging students with well-organized lectures, creative hands-on activities, and thought-provoking classroom discussions.
Thank you.
We now continue with Professor Sukumar Biswas Awards for Excellence in Physics for the year 2024.
The Professor Sukumar Biswas Award for Excellence in Physics 2024 is presented to Yash Vardhan for securing the highest score in graduate courses in the integrated MSc PhD program in physics. Yash Vardhan. The Professor Sukumar Biswas Award for Excellence in Physics 2024 is presented to Bipasha for securing the highest score in graduate courses in the PhD program in physics.
Professor Arnab is now requested to announce the names of TIFR Alumni Association Kaushik Medals recipients' names for the year 2024.
So the Kaushik medals for this year, the TIFR Endowment Fund and Alumni Association is pleased to honor Dr. Rahul Gera for his outstanding work to the paper entitled Trapping an Elusive Iron 4 Superoxide Intermediate Inside a Self-Assembled Nanocage in Water at Room Temperature and therefore awards him the Saraswati Kaushik Medal. The TIFR Endowment Fund and Alumni Association is pleased to honor Dr. Siddharth Bhandari and Dr. Shayantan Chakravarti for their outstanding work in the paper entitled Improve Bounds for Perfect Sampling of K Coloring in Graphs, and therefore awards them the Saraswati Kaushik Medal. And the TIFR Endowment Fund and Alumni Association is pleased to honor Dr. Mrinal Kumar for his outstanding work in the paper entitled Fast Numerical Multivariate Multi-Point Evaluation, and therefore awards him the Ramkrishna Kaushik Medal. Congratulations, Mrinal. Okay, so we congratulate all the recipients of PhDs, MSc degrees, as well as the best thesis commendations and the medals. So let's put our hands together once for all of them. Okay, there's one more. The TIFR Alumni Association Patent Award. The patent award for the year 2024 is to Professor Vivek Polshettiwar for his patent granted in 2023 for magnesium nanoparticles to capture and convert carbon dioxide to methane, methanol, or formic acid, or other fuels and chemicals. And he gets the TAA Endowment Fund and TAA Patent Award. Okay, thank you, and apologies if I've murdered people's names.
Thank you, sirs. I would like to invite Professor Bhaswati, convener of today's program, to deliver the vote of thanks.
This is once again, as I said on Sunday, a very difficult task, and I apologize at the very onset to those whose names I probably inadvertently would miss or have missed. I'm thankful to the Director TIFR, Registrar TIFR, Dean Graduate Studies, Dean Administration, Deputy Registrar Officiating for their support and guidance during the different stages of the organization of these events. I thank Professor Arnab Bhattacharya for taking up the mantle of conducting today's award ceremony at a short notice. Many thanks to Professor Vijay Raghavan for accepting our invitation to speak on this occasion. I thank the TIFR Alumni Association and the TIFR Endowment Fund Advisory Committee for their valuable support. My sincere thanks to the Office of the TIFR deemed to be university, particularly to Ms. Bindu Jose and Ms. Nikita Gudekar for preparing the entire material, the PowerPoint presentation, and the certificates for today's events. I also thank Dean Graduate Studies and Assistant Registrar Academic for overseeing the same. I thank Mr. Vinay Bhosle and his team from the PRO office for arranging the certificates and PowerPoint presentation related to the inputs from the TIFR Endowment Fund and TIFR Alumni Association. Thanks to Mr. Nitin Shirke and Professor Basudev Dasgupta for coordinating all these inputs. I thank Mr. Ajay Salve for his valuable support and Mr. H. Raghavan and the AV team for the arrangements in the auditorium, as well as those related to Zoom. I thank Mr. Gumaste and the Parks and Gardens team for the floral arrangements and garlands on both days. I thank the accounts, establishment, purchase, and store sections for their support. Many thanks to Mr. A.V. Tambe and Mr. S.R. Pavaskar and their team for arranging the food, high tea, and snacks for all the days. Thanks to Mr. Jatin Acharya and Mr. Vijay Shinde for taking photographs and covering all the events. I thank the electrical staff of technical services for their support throughout the program in the auditorium. I thank Mr. M.V. Raje and his team for the cosmetic arrangements. I particularly thank Ms. Sana Naim Sheikh for comparing the events on both 27th October and today. And I'm really happy to thank the support and guidance that I received from every member of the Apex committee, of the Apex committee. And I'm particularly indebted to the general administration team led by Mr. Nitin Sheke and very actively supported by Mr. Sanjay Rasam. Finally, I would like to thank the director TIFR for giving me this opportunity to be a part of the team organizing the Founders Day 2024. It has been an enriching experience for me. Thank you all for being here.
Thank you, Professor Bhaswati, for expressing our gratitude so eloquently. Thank you all for being a wonderful audience. Please join us for high tea in the cafeteria of the Homi Baba Auditorium. Thank you.